Thank you. Um, so, my name is Marta, and thank you for inviting me to this meeting. It's been very nice so far. I'm coming from Tokyo, from the National Institute of Informatics. This is our building where our group is, and this is our view. We have a view to the emperor's house, at least one of them, which is the Imperial Palace. It's a very nice location in the center of Tokyo. And also one of the reasons why I'm very tired today, because I arrived yesterday. So I get extra point for being here. I want to talk about this little work. It's not published yet, but it's on the archive. It's work with people from NTT and Tokyo University of Science and NII on simulating complex quantum networks using time crystals, which have been very trendy lately. So what we did basically was to use common tools from graph theory and apply them to periodically driven systems with the example of time crystals. But first of all, I wanted to introduce the team too. So you all know Kai and Bill. Victor was another one of the collaborators. He's a research specialist at NTT Basic Research Labs. Then we have Benjamin Renaust. He's a data scientist in Osaka University, even though he's moving now. And he was a very important contributor because he helped us build the graphs and visualize the system we wanted in the exact same way we wanted. And then the last collaborator is Tomo Osada from Tokyo University of Science. He's a PhD student that is going to graduate soon. And first of all, I wanted to have a thought about what a quantum network is and what it makes it complex. Because I realized there's not a strict definition of what a quantum complex network is. So I tried to make up mine. So classical networks are present, are much present in many fields, such as computer science, biology, technological engineering, and so on, because they are very useful tools to represent how different features relate, to visualize information, and to do predictions. So, however, not all the networks that we find happen to be complex. There's not a strict definition either about what a complex classical network is, but basically one of the definitions would be that a complex network is that network that, far from being regular or random, contains non-trivial topological structures that are present in many real systems. Systems such as neural networks, the World Wide Web, and this example here from Benjamin Renaust, which happens to be the thesis citation network he built out from his thesis. That happens to be a complex network, a scale-free network. So they have all things in common, such the complexity of the topology and the way the features of the network relate, and this can be translated in the degree distributions they present. So, for instance, scale-free networks tend to present the power law degree distribution. Also, they have similar dynamics inside the network and also resilience to structural and dynamical perturbations in the network. Another typical thing of those networks is that they present many hubs with high degrees, and other nodes with less degrees. So what a complex network is then? It seems logical that given how important the classical networks are in classical information and computer science, it was logical to find them very soon in the quantum arena. So the definition I made myself for a quantum network is a network that represents a quantum system somehow. And a complex quantum network is a network representing a quantum system that shows an emergent property such as a non-trivial degree distribution. So basically, the idea of classical complexity in classical network is the same than complexity in quantum networks. So typically, this is not unique, but typically the way we represent a quantum network is from two types. The first one is representing the nodes as qubits and the links between them as the presence or no presence of entanglement between them. And that's very common in large-scale applications such as quantum communications. So for instance, in this case, we draw a link between qubit 1 and qubit 2, representing that we have a bell pair between these two. The other way of representing a quantum network is by showing the links as real physical links. So the nodes are links according to the presence or no presence of a physical interaction between the qubits or whatever you want, atoms. And that's typically used for short-range quantum transport or to perform some quantum algorithm in, for instance, quantum chips, such superconducting chips. That example is, for instance, a work I'm doing with some students at the University of York, where they design different spin graphs to study the dynamics that happens inside the graph. And in that specific case, what they do with this graph is to generate a massively entangled pair between two of the nodes. But here, the links are physical interactions between such spins. But the type of quantum network I wanted to talk today is of a different type. So in this type of network, the nodes are configurations in the configuration space, in the Hilbert space of your quantum system, and the links represent the possibility of transiting from one of the configurations to the other one. So basically, what this network represents is the dynamics of the system, given that the dynamics of our quantum system will be like a one-particle quantum walk through this network. But first of all, before going in more detail with this type of networks, let's first go through the system that produced us, these networks, and how we arrived there. So the system we studied, as I said before, are time crystals. Time crystals have become very trendy and flashy because recently there's been a lot of investigations about it, and especially because they have been, for first time, realized in a lab. Time crystals are not too different from normal crystals in the sense that in a normal crystal, what we do is to break the continuous translation symmetry of the free space. And we impose a periodicity in our system that can be further broken by, for instance, placing atomic impurities. And what that does is to enlarge our period or repetition of our lattice. So the idea behind the time crystals is similar to this one, but instead of using the dimension of space, we want to use the dimension of time. So what we want to do is to break the time translation symmetry of time. But first of all, we need to break the continuous symmetry of time by by imposing some periodicity, some initial periodicity. A way to do this is to use periodic systems, such as introduced by a periodically driven Hamiltonian, for instance, or a Floquet system. In such cases, we can have a Hamiltonian that has an external drive that has a periodicity, or just the controlled application of cycles of consecutive operations, of consecutive terms of a Hamiltonian, such as this. But that after a period t repeats itself. So by doing this, what we get is a Hamiltonian that repeats its initial structure at every period t. So this way we are breaking the continuous symmetry of time. And at those multiples of t in time, or Hamiltonian is going to be always the same. So at those times, at those stroboscopic times, we can take the Hamiltonian as the time-independent Hamiltonian, because it's all the time the same. And we can study the dynamics at those stroboscopic times from that independent Hamiltonian. This time-independent Hamiltonian at those stroboscopic times can be obtained from the Floquet operator, which in turn is obtained from the unitary evolution, the unitary matrix that goes from 0 to t. And from that unitary matrix, we can obtain the Hamiltonian that's precursor of that dynamics, of that unitary, and that's the effective Hamiltonian, which is going to be time-independent and is going to be valid for all the stroboscopic times. So that's the basic approach we are following in this work. So as I said, time crystals have already been realized in lab. I think there's been 3 main experiments. I only remember 2 of them. One of them was done in trapped ions, and the other one was done using spin impurities in diamond. They all use the same formalism, the same Hamiltonian, and they all focused, I'm not sure why, in time crystals with periodicity 2. So what they do is they obtain a time crystal with a subharmonic response of twice the period of their drive. They drive their system using that sequence of operations, consecutive operations, and they get a response of the system after 2t. That's why it's called 2t. So what happens after 2t is that they get the initial state back. They have the revival of the initial state. So the operations they apply are, the first term of their Hamiltonian is a global pi rotation. They have a spin-half system, an interacting spin-half system. They apply a global pi rotation. They rotate everything in the x direction. They also have long-range interactions, and they also have random on-site disorder. And they initialize the system with all spins in the up state, and they rotate. And every period they rotate. So you need, of course, if you are applying only a pi rotation, you need twice the period of your overall Hamiltonian to go back to the initial state. So that's their time crystal. An important characteristic of time crystals, though, is that they happen to be robust against what they call an error in this rotation. So the time crystal is going to lock to this periodicity even when a small epsilon error is added to the pi rotation, to the global pi rotation that you do in your H1. So that's part of the idea of time crystals, this type of robustness and this lock to this, that locks the dynamical response in that periodicity. So what we did, based on this same system, sorry, I think I forgot. Yeah, the way they obtain the Floquet operator is just computing the unitary of these 3, of the consecutive application of these 3 Hamiltonians. So what we did was to consider the exact same system. We have, I think in this case, we have an 8 sites spin chain where we apply the initial pi rotation. We have long-range interactions and disorder. And as you can see, the dynamics takes twice the period of the overall drive, which is considered to be 1, to be unity. And it takes twice to go back to the initial state. That dynamics is the fidelity of the system against the initial state. What we do then is to, through Floquet theory, obtain our effective Hamiltonian, which is the time-independent Hamiltonian at stroboscopic times, and multiples of t, and it's obtained by doing the log of the Floquet operator obtained from the unitary from 0 to t. And then we represent this Hamiltonian as a type-binding model. It's that can be represented as the following matrix, because sorry, I'm sleepy. Yes, because the Hamiltonian can be described by the finite space of 2 to the n configurations. And once we represent this Hamiltonian in terms of a matrix, we impose a percolation rule, which is the one that decides whether we draw a link between the two nodes, two arbitrary nodes in our graph or not. As I said before, the nodes are configurations, and the links are the possibility of having transitions between these configurations. So that's the reason why we decided to apply this rule. And then we obtain the associated graph of that effective Hamiltonian. And this associated graph, when epsilon is 0, when we have no rotation error, happens to give us information about the order of the time crystal. So what we find when no epsilon is added, and we have a perfect birotation, is the presence of decoupled two-dimensional spaces in the graph. That means that our system only gets to hop between two configurations, your initial and the opposite, which is the rotated, which kind of makes sense. So if we initialize the system in all spin-ups, we only get a link from that configuration to the node that has all spin-downs. So you only get to hop between these two configurations, and you are decoupled from the rest of configurations. So that gives us the order of the time crystal. If we would want to study a time crystal with a different periodicity, such as a 3T time crystal or a 4T time crystal, instead of getting dimers, in the case of no error for the graph, we would get triangles or squares, and so on, and so on, and so on. So it's like a way of visualizing very graphically the crystalline order of your system. So again, I just wanted to emphasize, again, that the representation of the graph does not involve qubits as nodes, or entanglement, or physical links as links that bond these nodes. The nodes are configurations, and the links are the possibility of transiting between configurations, given that this condition is fulfilled. So what we did now was to start increasing the rotation error that we add in our first term of the Hamiltonian, of the periodic Hamiltonian. We know from previous experiments that this type of time crystal should be robust to moderate levels of epsilon. And we wanted to understand why, because really they never explain much why the robustness arises, or why, for instance, they always decide to initialize the system in a very specific way. So we wanted to see how our tool of representing the time crystal in terms of graph could help us understand this type of features in a periodically driven system. So we made this little video that shows how the graph of the system, of the effective Hamiltonian, changes as we increase the value of epsilon. Is it working? Yeah. So we see some generation of hops, and we also realized how things like to couple in a very specific way. That's why the colors are there, and I'll explain what the colors mean. And we also saw that up to a certain time, up to a certain value of epsilon, we always still have one isolated dimer. And that gives us a clue on why the system is robust. So yeah, at some point when epsilon is too big, we just get a massive, highly connected component, which is not interesting anymore because the crystal is melted. So that's what we called the melting of the time crystal. going from a very regular structure to something very chaotic. So up to around, maybe a little bit less, around here, we still have some decoupled dimers, or two-dimensional spaces. And those happen to, this one concretely, happens to be the one that contains the initial configuration, the initial state, and its rotated state. So that's why, at this point, the crystal is still robust, and the time crystal still exists, because that configuration is still decoupled to the rest. So it still doesn't see the rest of the configurations. And the colors are representing the number of domain walls, spin changes, in each of the configurations. So we realized that the graph, that the network was generating clusters in a preferential attachment way. And such preferential attachment is very typical, in fact, for complex networks. And it's very common to see it in scale-free networks. So once we realized that we had some type of preferential attachment and something was being a bit odd in the way this was evolving, we checked the degree distribution for some snapshots of that evolution, of that melting of the time crystal. When the error is moderate, we, in fact, have a complex network showing a scale-free behavior, because we get the polo degree distribution that characterizes this type of networks. And that's very interesting, because scale-free networks are very, as I said, are very common in many, many areas. And the study of the dynamics of scale-free networks is very interesting. But it's not very common to see any physical system that can, in the lab, give you a scale-free network, dynamics that's run by this type of complexity. So time crystals seem to offer this possibility at stroboscopic times and for moderate levels of this rotation error. So the reason why we still have the time crystal in order here is because we, as I said before, we have this dimer here decoupled. So that's containing the initial state and its rotated state. And I don't know if it's casual that the experiments choose this initial state, because if they would have chosen another one, they wouldn't have seen such robustness. So at least now we understand why the system is robust for that specific initialization. Once we keep increasing this error, the system becomes very chaotic, and it shows a highly connected component that presents a Poisson degree distribution, which is very typical for random networks. And this network is not very interesting anymore. So, as I said, up to moderate levels of epsilon, we have complexity, and when we get too far, we just get the crystal totally destroyed and starts being not interesting. So, yeah, the reason why we saw the preferential attachment I already mentioned, and I'll go through that a little later, but it's because we have a conservation of number of domain walls in the system, and I'll explain why later. But once we increase the value of epsilon, we break that, and so initially you have up to 8 domain walls, the possibility of having up to 8 domain walls in your configurations. And they happen to be quite degenerate for the same number of domain walls. Once you add the error, these degeneracies are lifted, and you create many, many, many transitions, and that's why things cluster the way they do. So configurations with similar number of domain walls tend to cluster to configurations with similar number of domain walls, and so on. And the last one to cluster is, in fact, the one that has 0 domain walls, which is the one with all spin-ups or all spin-down. So the preferential attachment that is observed through this domain wall clustering, configuration clustering, is the one that gives the complexity to the system. And this preferential attachment is the property of that's common in many, many, many complex networks, such as scale-free networks. These networks also show the long-tail degree distribution that I showed before with the power law distribution. And they tend to cluster like the more you forming hubs. So the more nodes one node has, the more it gets to connect. So the richer gets richer. So by looking at this, by using this tool, this graph theory tool, we were able to understand many things from tight crystals, such as robustness and how it melts, and also to understand the role of symmetries in the way the crystal melts. So we couldn't find the analytical expression of the Hamiltonian for the effective Hamiltonian as stroboscopic times multiples of t, because it's quite hard. So we had to do everything through numerics, through calculating the unitary and then finding the logarithmic of that matrix. But we can find the analytical solution for the stroboscopic effective Hamiltonian that happens at multiples of 2t. This is the one that gets invariant, because after 2t you recover your initial state. And that Hamiltonian happens to have this Ising interaction that conserves the total number of domain walls in your configuration. So, as I say, that's why initially, when no epsilon, when no error is present, you have everything conserved, and you don't get to get clusters in that situation. But once we introduce the epsilon, our system gets far from that ideal conserved expression, and we introduce this term that breaks the conservation of the number of domain walls. So this term is the one that induces the preferential attachment that we see in the melting. So a way we had to see how these symmetries affect the melting was to represent the matrix of the effective Hamiltonian in an increasing number of domain walls. So you have the subspace of the Hamiltonian, or your effective Hamiltonian, that contains only configurations with 0, 1, 2, 3, 4, 5, 6, 7 domain walls. And we wanted to see how how the off-diagonal elements were appearing, which are the ones that are causing the clustering in the network. And we realized that, in fact, the ones that appear first are the ones that cluster, that connect these nodes in the middle, which are the ones that have around half the possible number of domain walls. And then we get the other types, the other configurations connected to the rest. So those ones are the first ones to die, to melt, because there are, as I say, there are many, and by lifting the degeneracies, you get many, many, many transitions between them, and they create a hub. So they are the configurations responsible for being the hubs of the network. What we did to further prove that we had some transition going from a scale-free complex network to some uninteresting random network was to compute over 100 realizations, disordered realizations, the average degree of all the nodes based on the number of domain walls for all of the configurations. And we can see that we have a local maxima here that denotes a sharp transition between what's the scale-free behavior here and what's the preferential attachment here, and how this type of nodes get very, very quickly a higher degree, and how these ones still have a lower degree, which are the ones having the less number of domain walls, or the maximum one, and how this changes abruptly once we arrive to this epsilon, which was the top limit, where we were seeing a complex behavior, and how up to here we just have a normal random network, and everything gets, as I say, melted. So this type of structures, this type of visualization, and this way of approaching periodically driven or Floquet systems allow us to see transitions in the dynamics of the system. So, yeah, that I write them into the conclusions. So what we see is another type of quantum networks, and how this type of quantum networks can be useful to characterize not only time crystals and their related phenomena, but also the general periodically driven quantum systems. As an example, we showed how our strategy allows us to visualize the time crystal in order and understand a little bit better what the time crystals are, and understand the melting of the time crystal as an increasing error is introduced. We could also understand better the system and identify the importance of the conserved quantities, such as the number of domain walls in the configurations, and how the breaking of symmetries affects in the melting of the DTC. And also importantly, we show how for moderate levels of error, the associated graphs to the effective Hamiltonian of the time crystal with periodicity 2 show scale-free-like properties. And that suggests that these type of systems could be realized in a lab and serve as platforms to simulate this type of networks interested in many, many areas of technology and science. So that's pretty much it.
Okay, thank you very much. Questions? Simone?
So thank you for a very nice talk and for remaining not falling asleep. So I have a couple of questions. At the very beginning, you correctly said that typically when we think about networks, we put a link where an interaction is. Now, and then you do something slightly different, which is you put a link if there is a transition, possibility of transition, which somehow appears to me pretty similar, or at least the two things are not completely disconnected, so maybe you can elaborate, or you have some deeper thought than that. And second, I would like to ask how robust are your results if you change the condition, transition probability much bigger than the difference of energy, which is the condition for you to put a link, but I think that's also that kind of arbitrarily, and with system size scaling of the system. Thanks.
So, yeah, you're right. So if the possibility of transition is very similar to like having a physical link, but the thing is that this is not a real Hamiltonian, it's an effective Hamiltonian. So you don't have a physical link between those nodes. And also these nodes are not physical systems, are just configurations in the Hilbert space. So that's why it's different from having two qubits linked with some interaction. So that's what makes it different. About how the system changes with size. We've tried several sizes. Actually, I didn't mention, but this treatment here has been done for 8 spins, 9, 10, 11, and 12, and we saw the same results. So the system seems to behave in a very constant way, depending on size. And I think the other question is, that condition. So what's the question, sorry?
No, I mean, if you put a factor there,
What happens? So if we change that condition, the topology of the graph is going to change. We decided to choose this condition because it seemed to us that it was a realistic physical condition to consider, to think that you need to have at least a maximum, a bigger transition energy or a kick to go from one configuration to the other one. It has to be at least equal or bigger.
Probably depends with time, I would guess, right? I mean, so it's, if I imagine a transition between two states, a Rabi oscillation, then if you wait enough time between the two, but I'm not sure. So that's why I was asking. So maybe it doesn't change anything, but okay, thank you.
Yeah, I'm not sure.
I think here you can't wait arbitrary times because this isn't a stroboscopic picture. So basically these energies are always epsilon t or various things like this. So there are oscillations. So this, maybe you can wait 2t, 4t and change the order of the crystal, but that would be my guess, is that these quantities here are all effectively, they have a common t associated with them. So it is really an energy under a pulse, if you want to think about it that way.
Sure. So I just want to ask a couple of questions about generalizing this to other systems. So the first one is just a follow-up to this question here, which is that I can see if you change by a factor or so, it'll change which links are included, but it's not going to change the qualitative conclusions that you come to about domain walls and so on. But are there any other conditions that you know of that would change the graph topology, just because you mentioned that? And then the second question I have is that it was nice to see how the domain walls came out in the different colors appearing in the graph. Is there any way that you could have, so supposing it wasn't domain walls that were the key feature, but that there was some other thing hidden in the dynamics, is there any way you could go about looking at the different connected spin configurations and figuring out what condition it is that's actually causing the clustering?
I don't understand the last question.
Okay, so
Can you put it some?
So domain walls were applied as colors on your graphs,
Yeah.
and they sort of popped out as different different disconnected clusters up the top here. If it were not domain walls, but were some other condition that was common to the different configurations that are present in the cluster.
I see.
Is there any way? Have you thought about any way you might go about identifying what was common about different things that are present?
So you're basically asking if there's a way to characterize the clusters in the similar way we do with domain walls, but with another observable or something like that, some different characteristic of this type of states.
Yeah,
I don't know.
Okay, that's fine.
Nothing that comes to my mind at the moment, but maybe something.
And then the other thing was, have you thought about, are there different kinds of conditions that you might have used to get different topologies?
So if we change the condition related to the other question, if we change this condition, we might get, so I don't think it's going to change much, but maybe we don't get the same links that we get under this condition. For instance, if we, don't know, we would get a different topology if changing the condition, but I don't know how realistic that topology would be, how physical that would be.
Yes, I'm just wondering
if it would make any sense to change this type of condition, because as I said, I think that one is a quite physical one, right? To just consider links between states once the transition is possible to happen.
Yeah, I certainly think it's very intuitive from a physical perspective. I'm just wondering if, from the perspective of simulating complex networks, whether you could get other complex phenomena out of the system.
Yeah, but the nice thing of this type of complex network is it's actually giving you the dynamics of the system. If you change your constraints, that's going to have nothing to do with the dynamics of your system.
Yep, yes, I agree. So, but there are two things that you talked about, right? The first one was identifying aspects of a physical system that you're trying to study or to
and
engineer.
then simulating.
And then the second one was simulation.
Yes, but I still think that's the only condition you can have to have that type of simulation.
Okay, yeah, that's fine. That's my question.
So one condition I think you may be able to go to is exactly the opposite, Kij greater than the energy difference, because that's just a, that's a change of basis.
The dual of
space.
the, yeah.
So that should,
But
that's
that still makes sense, yeah.
Yeah, that's a relabeling in a sense.
Yeah,
So.
yeah, that still makes sense, yeah.
Okay. Sure.
So, is there a general systematic way? Can you hear me? Okay,
Yeah.
so if there is a general systematic way of determining the relevant variables that are needed to describe a complex quantum network?
So that's probably a question for Benjamin, the data scientist, but usually what you do is to just check the degree distribution of your network. If it has a long tail, or especially a power law distribution, that's a very good hint that you are dealing with a complex network. Also, the presence of hubs, that's also related to your degree distribution, are like a good hint that you are dealing with a complex network.